Hello, class, and welcome to Chapter 12, Section 1. This will be the last chapter we get through this year for the end of your chemistry for high school. We'll just get through Sections 1 and Sections 2 in Chapter 12 so that your final test on stoichiometry will just be on these first two sections of Chapter 12. So using equations and the arithmetic of chemical equations, everyday equations, how do you determine what you need to buy? For example, if you're going to the grocery store to get supplies to make s'mores with your friends, you need to determine the ingredients needed, like graham crackers, marshmallows, and chocolate. After you finish your ingredients needed, you determine how much of each ingredient you need to make one s'more. So we need 2 graham crackers, 1 marshmallow, and a chunk of 3 chocolates to make one s'more. 2 graham crackers, 1 marshmallow, and 3 chocolate squares to make one s'more. And we've written out our own type of chemical equation here. So let's go through a sample problem, 12.1, using a balanced equation as a recipe. How many pieces of chocolate would you need if you had 8 friends over and they each made a s'more? So let's list the knowns and the unknowns first, and we'll use the balanced equation to identify a conversion factor that will allow you to calculate the unknown. The conversion you need to make is from a s'more, which is graham cracker, chocolate, marshmallow, chocolate, to the number of pieces of chocolate. So the number of s'mores being made is 8 s'mores. So in total, you'll need 8 molecules of a s'more, 2 graham crackers, 1 marshmallow, and 3 chocolates. Does that make sense? It's asking us it's asking for how many chocolates we'll need if 8 friends come over. So if we're going to make 8 s'mores and the molecule for 1 s'more is 2 graham crackers, 1 marshmallow, and 3 chocolates, we'll put an 8 in front of it. The balanced equation then would be 2 graham crackers plus a marshmallow plus 3 chocolates would yield this 1 molecule of a s'more, which is GC2, big marshmallow, and 3 chocolates. So hopefully that makes sense. Let me go ahead and move my PowerPoint really up because it's just asking then for the number of chocolate pieces needed. As you can see there, that is our unknown. So the number of unknown is how many chocolates will we need then? We'll solve for the unknown by identifying a conversion factor that relates chocolate to s'mores, and you can write the 2 conversion factors relating the chocolates to the s'mores. So we know that for every molecule, for every 1 s'more, this is GC2, big M, CH3, that was 1 s'more, we need 3 chocolates. So that's a conversion factor. And we know, similarly, we can reverse that. For 1 s'more, we need 3 chocolates. So we'll solve for the unknown. The desired unit is chocolate. We want to know how many chocolates are at the end. So you'll use the conversion factor on the left, and we'll multiply the number of s'mores by the conversion factor. So we want 8 s'mores because we have 8 friends, and we'll multiply by the conversion factor so that this GC2MCH3, our molecule name for a s'more, will cross out. And then we'll just multiply 8 times 3 to give us 24 pieces of chocolate we will need for those 8 friends that are coming over. Does the result make sense? If 3 pieces of chocolate are required for each s'more and you're making 8, then 24 pieces of chocolate sounds like a correct answer. The unit of the known GC2MCH3 cancels, and the answer has the correct unit in chocolate. So that's kind of a silly example, but it's useful and to try to explain how then we can use that same concept with chemical equations. So chemists use balanced chemical equations as a basis to calculate how much reactant is needed or how much product will be formed in a reaction. And when you know the quantity of one substance in a reaction, you can then calculate the quantity of any other substance consumed or created in the reaction. The calculations of quantities in chemical reactions is a subject of chemistry called stoichiometry, and it allows chemists to tally or number the amounts of reactants and products using ratios of moles or representative particles. Balanced chemical equations can be interpreted in terms of different quantities by the number of atoms, the number of molecules, the number of moles, the mass, and the volume. So the number of atoms, so at the atomic level, a balanced equation will indicate the number and types of atoms that are rearranged to make the product or products. For example, we have 2N2 is nitrogen gas, plus 3H2 is hydrogen gas will form 2NH3 as a gas. In this reaction above, you have 2 atoms of nitrogen plus 6 atoms of hydrogen will yield 2 atoms of nitrogen and 6 atoms of hydrogen. Because remember, in a chemical equation, we can never create or destroy matter. The number of molecules, you can always use Avogadro's number, which again is 6.022 times 10 to the 23rd molecules, to then figure out how many nitrogen and hydrogen molecules will react to make how many ammonia molecules. So we'll take one nitrogen molecule, so 1 times 6.022 times 10 to the 23rd molecules of nitrogen. Then we'll take 3 of the hydrogen gas molecules, so we'll do 3 times Avogadro's number to yield 2 times Avogadro's number. The balanced chemical equation will tell you the number of moles of both reactants and the products. In this reaction above, for example, you have 1 mole of nitrogen plus 3 moles of hydrogen, yielding 2 moles of ammonium. In the mass, a balanced chemical equation will obey the law of the conservation of mass. And remember that mass can neither be created nor destroyed. So in this reaction above, you have 28 grams of nitrogen, because that's what each nitrogen atom equals from the mass from the periodic table. So you take it 14 plus 14. Then you have 3 times 2 grams of hydrogen each to yield 2 times 17 grams of ammonia. So we see that 28 grams of nitrogen plus 6 grams of the hydrogen, that will equal 34 grams of ammonium, because we can never create or destroy matter. If you assume standard temperature and pressure, the balanced chemical equation also tells you about the volume of gases. And remember that 1 mole of any gas at standard temperature and pressure will occupy a volume of 22.4 liters. In this reaction above, you have 1 mole of nitrogen, so you have 22.4 liters of nitrogen, plus 3 moles of the hydrogen gas. You take 3 times 22.4 to end with 2 moles of ammonium. So you'll take 2 times 22.4. And you'll see that when they are equal, we get 22.4 plus 67.2 is equal to 44.8. Let me go through that because that is not an equal amount of number. Let me come back to that, guys. Let me come back to that one and I'll give you a little updated in the video on this problem. Using a balanced equation as a recipe, hydrogen sulfide, so we're going through another sample problem. Hydrogen sulfide, which smells like rotten eggs, is found in volcanic gases. The balanced equation for the burning of hydrogen sulfide is 2H2S as a gas plus 3 moles of oxygen will yield 2 moles of SO2 plus 2H2O, all as a gas. We need to interpret this equation in terms of the number of representative particles and moles, then the masses of reactants and products. So let's identify the relative concepts first. The coefficients in the balanced equation give the relative number of those representative particles and the moles of reactants and products. And a balanced equation, chemical equation, obeys the law of the conservation of mass. And we'll apply the concepts to this situation. Let's use the coefficients in the balanced equation to identify the number of representative particles and moles. So we have 2 molecules of H2S plus 3 of O2 will yield 2 molecules SO2 plus 2 molecules of H2O. And we can write that as 2 moles of H2S plus 3 moles of O2 will yield 2 moles of SO2 and 2 moles of H2O. Remember that atoms and molecules are both representative particles, and in this equation, all of the reactants and products are molecules, so all of the representative particles are molecules as well. Now we'll use the periodic table to calculate the molar mass of each reactant and product. 1 mole of H2S will add up to individual hydrogens molecular weight plus the sulfur molecular weight. So 1 mole of H2S is 34.1 grams of H2S. 1 moles of oxygen at 16 plus 16 for the molecular weight is 32 grams of oxygen. And 1 mole of SO2 is 64.1 grams SO2. 1 mole of hydrogen, 1 plus 1 plus 16, those are the molecular weights of hydrogen, 2 hydrogens plus an oxygen is 18 grams of H2O. Multiply the number of moles of each reactant and product by its molar mass. So remember, we have 2 moles of H2S, 3 moles of oxygen, 2 moles of SO2, and 2 moles of H2O. So we'll take that 2 moles times the molecular weight, 34.1, plus 3 times 32 will yield 2 times 64.1 and 2 times 16. When we do that, we cross off the labeling. So we'll be left with grams. So we'll get 68.2 grams of H2S plus 96 O2 will yield 128.2 grams of SO2 plus 36 grams of H2O. And we see that the grams equal each other because matter can never be created or destroyed. Hopefully that was helpful, guys. We'll see you for our last and final lesson on lesson 12.2 next week. Take care, everybody.